Thank you. It's pretty scary. It's a full house like that. Stand up and talk in front of all of you is scary and exciting. So thank you very much for being here, for coming. I'm going to talk about time. So I'm going to try to tell you in the simplest way I can everything we have learned about the nature of time, everything all the many things we do not understand about the nature of time, and a few ideas which might be right or might be wrong, and I'm not sure about them. So this is about time, 45 minutes for trying to clarify where we are in our understanding of time. Now, why there is something to say about time. Let me start from this. If I just forget what I learned as a physicist and think what usually time means for me, I think for many of you as well, time is like a long sequence of events, a long line of things that happen in one after the other, along which the history of the universe unfolds. So this is a metaphor of time, a long, long line. I bought this morning. And we are at some moment of time, say here. I had a pen. So this is where we are. And this is the future, this is the past. So this is a few minutes in the future. This is where I have to end this conversation. This is when you were coming in. This is this morning when you woke up. Yesterday, the day before, 10 years ago, the Big Bang, maybe, who knows, there. And the future, who knows, even that. Brexit at some time or whatever. Something will happen. Obviously, the future, it's very different from the past. In some sense, we move. In fact, we have just moved a little bit. I'm just here now. And obviously, we're all in the same present. So this is the present. We're all together in the same present. And right now, the universe is in this present. So right now, the entire universe is here. Tomorrow, the entire universe will be here. The entire universe change like that. And of course, between two moments, say now and tomorrow, there is a certain amount of time, 24 hours. And that's 24 hours for everybody. That's a time difference between this moment and this moment. So this is time in our everyday life, a long line, a sequence of moments of time that we can order, which has a preferred direction, past and future are very different, that we can measure. We have clocks, we have watches, we have clocks to measure it, and we all agree about the time intervals between two different moments along this line. Good. So almost everything I've said is wrong. It's really factually wrong. Like if I said the Earth is flat. It's not flat, it's wrong. The Earth is a sphere. Time does not work this way. It works in a different way. Of course, to some approximation, if we forget something, it works this way. But if we look at closer, if we have better clocks, if you look into small, if you look into large, time is not this line, is not a unique sequence of moments. There is no sense in which the universe is all in the present. There is no sense in which between one moment and the other there is a time difference which is the same for everybody, and so forth and so on. These are not speculative ideas of strange dreams of the physicists. These are facts. Facts that we measure in the laboratory, we measure with instrument, and can be checked. So what I'm going to do is first of all describe this fact to you and show why this picture of time is wrong. And then I will tell you what do we think is time at this point. So if you take away pieces of this picture, what remains, what is the remaining idea about time that we have. And then in the last part of this conversation, I'll tell you how, from this world without time, we can come back and reconstruct this idea of time for us. Okay? So, first part is what's wrong with that. And I will list 4 things, 4 facts that show this picture to be wrong. 3 are very, very solid. All my colleagues and I will all agree on that. All the physicists agree on that. Even the chemists agree on that. And nowadays, in the engineering idea of that. The 4th is much less clear, but is pointing in the same direction, and I'll mention it. Let me start from the first one. First one is very simple, and maybe you know about this. This is my watch. It's a good watch, and I always need a second watch, so I asked Valerie if I could borrow her, and I borrowed her watch. So these are 2 watches, and they indicate exactly the same time, 4:32, 4:32. And of course, you know that if I move one watch, I put it higher, I wait a little bit, 1, 2, 3, and I bring it back, they still indicate the same time. They both have moved. But this is because these are not very good watches. If you do this with very good clocks, and today we can do this with very good clocks, because we have very good clocks, you move one higher, wait a little bit, you bring it down, and this is ahead, this is behind. So I repeat, here there is more time. If you think we're moving on this timeline, if you move up and wait a little bit and then come down, the clock up has measured more time than the clock down. And it's not just a matter of clocks. Everything. I mean, if you're high, you have more time to think. A flower will blossom more. A machine would do more cycles. There's really more time, more things happening up than down. Of course, the difference is small. Otherwise, we would have noticed it clearly earlier. We had to wait for having good clocks for measuring it. But quite remarkably, this was understood before having good clocks. In fact, this was understood 100 years ago by Einstein. It's one of the great intuition by Einstein. In 1915, he completed this theory, general relativity, where makes this very clear. At the time, clocks were not good enough for measuring it. So at the time, it was a theory, a good speculation that seemed to put things together. Today, it's not a theory, it's nothing to do with Einstein. It's a fact that we measure in the laboratory. In fact, it's so clear and definite that technology today needs this to be taken into account. You probably all use one way or the other GPS, navigator, the thing in the car, or the computer that on your telephone that tells you where you are. It works with satellites. It gets message from satellites. On those satellites, there are clocks. So essentially, the satellite broadcasts the time, and your little device uses the time to triangulate where you are exactly. And when this was built, the physicists told the engineering that were putting up the system, careful, because up there, your clocks are going to run faster than down here. Because up there, there's more time than down there. The engineering, who trust the physicists, of course, said, yes, of course, we're going to do that. The entire project was controlled by the American Army, because the GPS was made, it belongs still today to the American Army. And so it was supervised by the generals of the American army. The generals looked at that and said, what's this story of the time goes at different speeds? I didn't believe it. So the first satellites were put up there with a switch which could or could not take into account this fact, the difference of speed of time. And of course, it did not work. It does not work at all if you don't not take this into account. So it's a hard fact now, our technology would not work. We would crash the car against the wall driving with a navigator if we didn't take into account this. This means that the time between this point and this point is 24 hours here, but it's 24 hours and something if you're higher, and more if you're more higher, and less if you're less. Now, here on Earth is small. This effect is small. We're talking about nanoseconds. It's measurable. In fact, now it's measurable at 30, 40 centimeters of altitude in the lab. But it's small. You need big clocks. But if you go near a bigger mass, what makes the difference is the mass. It's mass of the Earth. So the Earth is a big mass and it slows down time. If you go to a bigger mass, like Jupiter, it's stronger. If you go near a big star, it's stronger. If you're near a black hole, we know that the universe is full of black holes, it's even more strong, so strong that very near to the black hole, time essentially stops down. Goes very, very, very slowly. This means that if we had a starship, we could move near a black hole, stay there for half an hour, and then come out. Outside, hundreds of years could have gone. So we would come away from the black hole into the far future easily. If you have seen the movie Interstellar, the hero comes back on Earth and finds his daughter much older than him. And that's not an Hollywood fantasy. The scientific advisor of the movie was Kip Thorne, who's a great relativist who got the Nobel Prize because of the gravitational wave detection. And he checked all that. So the story is realistic. The only non-realistic thing is that we don't have the money for building the starship and coming back. So time is far more elastic than our intuition of this rigid passage altogether. The time interval between one point and another point depends on where you are. And that's the first fact that makes this intuition about time wrong. Second fact. This is also something very clear, very established, very accepted, but perhaps is the most striking, in my opinion, is the most striking discovery in modern physics, and maybe even in modern science, together with Darwin, probably. The fact is simple, but the consequence is astonishing. The fact is that the time difference between two clocks does not depend only on where they are, but also on how they move. So if I take two clocks, I move one, okay, I come back. This has measured less time than this one. So this is ahead, this is late. So if I move fast, I have less time. So slow down. Don't move much. Again, it's a small effect. You have to move very, very fast to be important. You have to go the speed near the speed of light to be remarkable, but it's true. A consequence of that, which is not immediate, you have to work out, you have to do drawings and convince yourself, but it's a consequence of that it is impossible to say clearly when is the same time in two different points. See, imagine that I stay here and my sister goes somewhere else. And then we want to say, I want to think, what is my sister doing now? Well, half an hour has passed for me, half an hour later from the separation, what is my sister doing? But half an hour later from the separation for her can be something else that's half an hour for me. If one of my sisters have moved fast and the other has moved slowly, they meet. And for one is half an hour, for the other is 45 minutes. So when is the now? You can say, well, I send a signal to her, I look at her. I can look at you and say, I see what you're doing now. But wait a minute. When I see it, your light comes from you to me. It takes time. So I don't see you now. I see you in the past. I'm seeing all of you, not now, in a little bit in the past. You're not seeing me now. You're seeing me in the past with respect to what you see. And I see you in the past. So we're not in the same now. Well, I mean, light takes, 4 or 5 nanoseconds to go from here to there. Nanoseconds, very, very small. But if you were on Jupiter, it would take a good hour light to go there. I don't know. I mean, it's for 15 minutes to Mars, more to Jupiter, depending where they are in the sky. So it would be impossible to... I cannot see somebody in Mars in the moment in which this person sees me because there's 15 minutes. And if I try to come out with a story to say when is exactly the same moment, it turns out, because of this dependence of the time on the speed, that there is absolutely no way of doing that. The consequence is that, literally, it makes no sense to ask what is happening in the far distant universe now. And let's sink this in, because this is, for me, as I said, the most astonishing discovery in modern physics. The notion of now is very clear to us, right? We are now here. But now here makes sense at a small distance. Now all over the universe does not make any sense. Now is a local notion. Now is a bubble around us. How big? Well, depending on our resolution of time. We perceive time, we can perceive a fraction of a second, I don't know, a tenth of a second. That's the smallest time we can perceive. So in a tenth of a second, light goes quite far away. Well, that's our now. Beyond that, there is no way to accord time in an objective way. So time is not a single line. Every bubble has its own time. Every object moving has its own time. It's not a single line. It's a complicated structure of things that move differently. Each one has its own time. And of course, they communicate. I can send signals to Mars, Mars can send signal to me, but we cannot think that we're all together in a single time. It just doesn't work. 2. Third one. Now, the third one is in a sense, is the most disturbing. It came as a surprise slowly in physics. One of the things I said about time is the past is very different from the future. It's totally obvious to us, right? I remember what I did yesterday. I don't remember what I did tomorrow. I have a picture of myself as a boy. I don't have pictures of myself as an old man. Well, yeah, I don't have pictures of older than now men of myself. So it's no doubt. We have traces of the past. We have memories of the past. We have information about the past. The future is open. Who knows what's going to happen in the future? Good. So this is so clear that it was a big surprise when slowly it became clear that the laws of physics have a hard time of distinguishing the past from the future. When Newton wrote the basic law of physics, the laws of physics are the same for the past or for the future. So whatever can happen in one direction can happen also in the opposite direction. If you take a movie of something satisfying the law of Newton and you show the movie in reverse, that's still possible. Then came, the electromagnetism of Maxwell, came quantum mechanics, quantum field theory, general relativity, Einstein theory. These are all theories which do not distinguish the past from the future. And it doesn't make any sense because these theories describe our world well. And in our world, there is past different from the future. Where does the difference come from? Well, there is one piece of physics where there is an equation that distinguishes the past from the future, and that's the science of heat, of temperature. So there is one equation, one fundamental equation of physics, which make a difference between the past and the future, and it's an equation about heat, about temperature. It's the famous second law of thermodynamics. Entropy, I'm going to talk about entropy a little bit later, entropy will always grow, doesn't decrease. And it is a fact, I don't know why it's not more talked at school, this fact, but it is a fact that every time in a phenomenon there is a distinction between the past and the future, there is some heat, there's some temperature. There's no distinction between the past and the future unless there is heat and temperature. Let me give you an example. If I have a pendulum, and I study a pendulum. I'll make a disaster, I know. But, I'll make a pendulum here. Please don't break. So I study this. I make a movie of this, okay? I show the movie backward, and you don't see which one is the right one. It moves like that. If you look at backward, it's the same. You make a movie of the solar system, the moon, the star. You show the movie backward, it's still reasonable. But if you wait a little bit, after a while it stops, it slows down. Now, if you make a movie and you show the movie backward, you say, no, something is wrong because this doesn't start by itself. But when it slows down and stops, it's because there's some friction, and friction generates heat, right? So it's the heat that distinguishes the past from the future. If I throw something and it stops, right? If I throw this, it stops. If I take a movie and see it moving by itself, say, no, that's wrong. So something that stops distinguishes the past from the future. And again, there's friction, there is heat. So the distinction between the past and the future has to do with heat and temperature. And what is temperature? What is heat? It's the molecules moving very fast. So what happens when this slows down and stops? It happens that the energy of its motion goes to the energy of the molecules. So the single energy of one moving object is passed to the energy of many, many, many molecules. It's like spreading something around. And the ordered motion of all these molecules together becomes a disordered motion of all the molecules heated. And that's the only source of difference between the past and the future. Things get disordered. Everything that distinguishes the past and the future, including us becoming older, it's always, from the physical point of view, something where there's order disgregating and getting in disorder. That's a physical meaning of the second law of thermodynamics. That's the only thing that distinguishes the past from the future. Which is very good because we have understood something, but it's also very puzzling because this enormous difference between past and future, memories, traces, has only to do with the fact that things were ordered in the past. And who ordered them? Why they were ordered? What does it mean? We don't know. That's one of the most debated issues by physicists, by philosophers of science. I'm going to a conference in New York in a month just to debate these things. What is the meaning of this initial order? Because the universe started up in a special thing, what does it mean? But clearly, this distinction between the past and the future is much less fundamental than what looks like. It's not something about the basic working of the world. It's something about the way things are ordered. So you see, this clearly line, past, future, equal time for everybody, fundamental distinction between the past and the future, it's just blown up. Fourth and last dissolution of the notion of time, it's my own work, it's quantum gravity. I work in quantum gravity. We know that the structure of time is governed by gravity, and I gave you one example. The Earth, the big mass, slows down time. The gravity of the Earth, the key effect of the gravity of the Earth is to slow down time. Every mass of the universe slows down time around it. In fact, in general relativity, things fall just because time is, goes slower down than up. We understand falling in terms of the slowing down of time. Good. That we know well. What we do not know well, and that's the field in which I'm working, quantum gravity, it's the quantum properties of gravity. Quantum mechanics is this funny, strange theory that does describe very, very well the working of small things. And when we apply it to gravity itself, we're still in the dark. But what seems to be obvious is that in the small, the strange quantum properties that small objects have also affect time. Which means there was this morning in the news, one little experiment down in Australia was published in these days, so it got to the news. Perhaps some of you saw them, in which they made something happening, some event A, and then some event B, but because of quantum mechanics, each one fluctuates. So the actual situation is like this happening first and this second, but also vice versa, because time goes a little bit in this direction, a little bit in this direction. So quantum mechanics implies sort of small fluctuations of everything. You know, particles like a wave is not precisely defined, and time itself is not precisely defined. It's small, it fluctuates. The idea of a single time variables in terms of everything passes just doesn't work anymore. So, in my work, I try to write down equations that describe the world, keeping into account everything we have learned, general relativity, quantum mechanics, thermodynamics. And what we do, me and a lot of my colleagues, is try to write this world and just forget time completely. Time is not a good notion when you go to the fundamental grammar of the world. It's an approximate notion. It's a local notion. It's a notion that has to do with our daily life. It's good at our scale. It's not good everywhere. There are many things like that in physics. Think about up and down. That's up, that's down. Totally obvious, totally clear, uncontroversial. But many of you remember physics of high school. In the Newton equation, there's no up and down. In the universe, there's no up and down. When the astronauts go out, were flying to the moon, the astronauts were in their capsule, right? They were all floating around like that. And if one says to the other, where did I put the bread? He says, in the drawer, which one? The one up. What do you mean by up? There's no up here. So up and down make no sense in the universe. They make sense here. Why? Because there's a big mass, the Earth, and down means toward the Earth. So we understand up and down perfectly well. And of course, in Sydney, up is the other way around with respect to us. Up is that way in Sydney. So time is something similar. It's not something universal, common to the entire universe. It's something local that something produces it. At the fundamental level, and these are the equations that I use in my work, we write this equation and there's no time. There's no t variable. This takes me to the second part. How do we think about the world without time? So how do I do physics? How do my colleagues do physics with equations where there's no time variable? And let me try to take away a confusion, first of all. No time does not mean that everything is iced and not moving, blocked, frozen. It's the other way around. Something which is frozen is something that does not move while time passes. Right? It's the other way around. So, in the fundamental description of the world, things happen, everything happens, but it's not ordered in time. So try to visualize a lot of little events disconnected to one another or loosely connected with one another, but they don't sing together like an orchestra with a single director that beats the time for everybody. That's the world at the fundamental level. Of course, we can have a clock, but we can have 2 clocks, which beat different times, or 3 clocks, or 4 clocks. Everything that moves can count as a clock. We can use it as a local clock for locally and in some sense asking how other things change with respect to that one. So every single event or sequence of event can be used as time, but there is no preferred time all over the universe. That's the physics in which I work, quantum gravity. No time. And in particular, since there is not a unique time, since there isn't a preferred time, identification of events at different times is not natural, don't work. Which means, and I've already gone there in a sense, and that's the key point, that at that level, I think we should think of the world not as a set of objects. What is an object? An object, pen, is something that now is a pen, now is still a pen, now is still a pen. Okay? If I wait 10 minutes, it's still a pen. So it's something which lives through time. Objects are things that remain through time. They remain themselves through time. But from the point of view of physicists, nothing really remains through time. Okay? This is some molecules that for a while got together and then they will disaggregate. So this is really an aggregation of molecules, is a process, is a sequence of events, a set of events, which means it's much better to think of the world in terms of event, happenings, not in terms of things. And I think this is a deep lesson from modern physics, in my opinion, that we think better of the world in terms of happenings rather than in terms of things. You know, a war is a happening, a sunset is a happening, is a process. I am a process. I keep changing. We are processes, a human being. If we try to block entities, think in terms of entities, we get confused because entities dissolve and come together from other entities. But these other entities themselves come together from other entities. If we think in terms of events and set of events that make processes, the world makes more sense. So, absence of time at fundamental level does not mean frozen. The other way around. It means happening, a lot of disordered happening. So that's the world, I think, that is emerging from contemporary physics. Not a single time, no time at all, events, relation between events, an equation that describe how these events happen with respect to one another. Good. I've done half of my way. I've taken this image of time, I've killed it, destroyed, all the way through, until this sort of timeless world, which is just events without a preferred time variable. But I'm not done, because now I have to come back. I have to tell you, where does this idea of time come from? Where does a line come from then? Where does the past and the future come from? Where is the idea of this flowing of time come from? And that, I think, is the most beautiful part of the story. Where is our sense of time in this universe, where there isn't a preferred time, there is no time variable at all? And I think the answer is not a simple answer, it's a step-by-step answer. So from the equations of quantum gravity, where there's no time at all, you can see that there are approximations, special situation, regimes, physical situations in which something resembling this line is approximated. Think about up and down. There's no up and down in the universe, but if you have a mass, if you have things moving on the surface of the mass, with respect to them, with respect to a point, you can talk about up and down. So the second part of the story is start from a world without time and try to understand where our notion of time comes from. And the answer, as I said, is multi-step. First of all, let me list some of these steps. First of all, quantum gravity, which is my field, describe the world in the very, very small, but we don't see all this very small. We see just large average. The quantum gravitational world is a world in the very small, and we don't see there, so our vision of the world is very blurred, it's very imprecise. If the astronauts, when they got to the moon, they looked at the Earth, they see a blue, shining little ball, nice and uniform, with this little collar. Simple, okay? They have no idea, they don't see that in this little ball, you know, there is all of us, London, and people talking and all this, and when we see it just as a drop of water, we just see one little shining drop of water. We don't see the millions of zillions of molecules that jump around. And in fact, within each molecules, there are zillions of little quanta of space dancing around. So the universe is incredibly complex, and we have access only to a teeny, imprecise, foggy version of it. And it is in this fog, this imprecise version, that we start seeing something that resembles our usual space and our usual time. And something that happens in this foggy, this blurred version of reality is that we lose control of a lot of reality. And remember what happened with the molecules, with the friction. We call heat the motion of the molecules which we don't see anymore. We see energy disappearing into heat. So the notion of heat exists because we have this blurred version. It's not in the thing, it's in our blurred version of the things. We wouldn't talk about heat and temperature if we saw the single molecule moving. They just move. There's nothing hot in things that move. Okay? So just energy of the molecules. So this means that when we talked about thermodynamics, we're really talking about heat and temperature. We're really talking about our blurred version of the world. Not because we are not natural objects. We as natural objects, we interact with a glass of water, but only a few variables, not all the variables. And in this simplification, we average over things. We have this blurred version, and it is this blurred version that distinguishes the ordered motion from the non-ordered motion. So you see, the difference between the past and the future has to do, I think, with the way we interact with the world. Is not just in the world, it's in the perspective between us and the world. And science in general, very often has understood, has solved strange questions, deep questions, by realizing that we make a mistake when we think that something is there, when it's really in the relation between here and there. Think about one of the most beautiful shows in nature, which is the sky that turns around us, right? You see the sun going up and going down, the moon going up and going down. If you go out in a night, in a clear night, not in London, you see all the stars that move during the night. They make a piece of a circle during the night. In London, probably you don't see any star, I don't know. But if you just walk out in the countryside, you have this wonderful show. And then you ask, why is the universe turning around us? And we have understood. It has taken only 2,000 years, but we have understood why the universe is turning around us. It isn't turning, we are turning. Okay? We sit on a rock, and this rock happens to be spinning, and that's why we see everything turning, because we are. Okay? This does not mean that it's false, or is illusory, or is spiritual, or is illicit. No, it means it's perspectival. So we understand the turning of the sky by looking at ourselves and seeing the relation to other motion and the rest of the universe. So we understand in terms of the relation between us as physical objects and the star and the moon and the sun as physical objects. And the same something like that has to do with time. The passage of time, I believe, has a perspectival aspect with it. It has more to do with the way we interact with the rest of the world than by the world by itself. Not because time is false. It's not false that the sun rises and sets. It's just we understand it not just by looking at the sun, but looking at how we move with respect to the sun. And let me make the two last steps, which perhaps are the two most beautiful. For us, time is flowing, it's passing. What does it mean? I insisted a lot in saying that the difference between the past and the future is that we have memories of the past. We know about the past. Of course, this is possible because of thermodynamics, because of physics. But if you think for a moment, for us, the time is not really the clock that goes around. It's exactly the memories of the past. When you think about the past, you're thinking about what you remember about the past, or what you have read about the past, or a movie you've seen about the past, or a book of physics or history that you've read about the past. So, for us, when we talk about time, we're really talking about that we remember the past, and we can anticipate the future. And this, I think, is a very deep intuition that goes back to philosophers, in fact, goes back to St. Augustine, who wrote a very famous text on the nature of time. He was saying, he was talking about music. He was saying, when I listen to music, there's a musical phrase, it's beautiful, it's marvelous. What am I really listening to? Because in every single moment, I hear only one note. There's a melody, a chant. I hear one note. How do I know about the others? It's only one single sound which is there. What about what happened first? And then St. Augustine realizes that the music exists because at each single moment we have somehow retained in our mind the rest. And in fact, we even anticipate what's coming out. So we grasp something about the past and something about the future together. But that has nothing to do with physics. That's our brain that does it. And the people who study the brain in neuroscience are telling us, I'm a physicist, I'm not a neuroscientist, but I'm crazy about reading neuroscience books because it's fantastic what's happening in neuroscience. They're telling us that the brain does exactly that. The brain is like, does all sorts of things. It's a machine that the most important things it does is keep learning, it keeps absorbing memories, it keeping be connected to something outside and keeping this, such that in every single moment the brain has memory of the past and try to compute the future on the basis of this memory of the past. So the brain is this machine connected to the outside, which constantly work between something here and something there, and that's the time for us. The time for us is memory expectation. And artists have often insisted on that. There's this marvelous book by Proust. The French title is La Recherche du Temps Perdu, which the exact translation is looking for lost time, searching for lost time, the exact translation of the title. And the book is a huge novel. All sorts of things happen, but it's not presented as a story of happening. It's presented as everything that the main character, his name is probably Marcel, remembers. So it's 1,000 pages of description of what is between the ears of Marcel, what is inside here. That is where time is. Time is here. It's not out there. It's our memory, our expectation. And so in this reconstruction of time, to go to understand what time really is, you shouldn't ask physicists only. Of course, physicists have their say, but you should also ask people doing thermodynamics, psychologists and neuroscientists to understand that's where the answer should be. It's like, when we understood colors, colors have nothing to do with Maxwell equations, have something to do with Maxwell equation, light. But the reason we see three colors and combination of three colors is because our cells in the eye, receptors, are of three kinds. It's nothing to do with physics, it has to do with us. So the nature of time has to do with physics, but has much more to do with the way our brain works. And the last step I want to get to, and it's going to be my last point, and perhaps is the most important of all for understanding the nature of time, is this. Time touches us. Is not a neutral notion for us. Why? Because, time passes. We live in time. We are time, in some sense. We can't even imagine ourselves without time. We are this memory and this anticipation. If I destroyed completely my memory, I wouldn't remember even me 3 seconds ago, I wouldn't be myself. Because myself, I'm this narration of myself. But this narration of ourselves, this story of ourselves, it's also not only our identity, but also the source of our good and bad emotions about ourselves. There is a key core teaching in Buddhism, which always I found telling, which is that life is sufferance, but the reason for which life is sufferance is because we cannot accept impermanence, which meaning the things passing, things that go away. We suffer because we lose things, because we think we don't have, we might have, we think we have, we will not have, we will lose. We're going to die. That's time for us. Is what takes away everything to us. So it's hard to think about time without instinctively and immediately be connected to what time makes to us. Not only it makes us, but it destroys us at the same time. We are in time, and at the same time we're destroyed by time. So there is this emotional component in our sense of time. But I think that this emotional component is not really some foggy emotions that blinds us with respect to the clarity of doing science about time. It's the other way around. This emotional component is, to a large extent, precisely what we're talking about when we're talking about time. Because the sense of flowing of time, which is so hard to find into physics, there's nothing flowing in a physical equation, is so hard to find into thermodynamics, even neuroscience. It's completely clear when we think about our emotional relation to time, this passage. We are this thing that keep remembering, keep anticipating. So our own perception of what time is. This time, I have to finish. Time is passing. It's over. 50 minutes are gone. That emotion of time is exactly what time is for us. So we should not forget it to try to understand time only in physical equation. If we do that, we understand something and we feel that something is missing. And what is missing is precisely our emotion of time, this deep emotion of time, which makes us and destroys us. So to a large extent, I think the emotion of time is not the fog that makes hard for us to understand time, but it is precisely what time is for ourselves. And I'll stop here. Thank you.